Here is an example vertical sag curve problem where we're given a 600 equal tangent sag vertical curve. And in this case, we're told that the PVC, point of vertical curvature, is located at station 170 plus 00 with an elevation of 1,000 feet. So remember that the PVC is the beginning of the vertical curve. The initial grade is minus 3.5% and the final grade is plus 0.5%. So it is indeed a sag curve. And we're asked kind of classically to find the elevation and stationing of the other 2 points, the PVI and the PVT, and then also to identify the station and elevation of the lowest point on the curve. So basically, we can draw a picture. So this shows the 600-foot vertical curve, and I usually try to draw the slopes approximately to scale just to so that I get a clear picture in my mind of what the curve actually looks like. So as you can see, in this case, it's somewhat of a lopsided curve with a much steeper slope on the initial side and a flatter slope on the final side. So I always want these tangents to extend. So in order to solve this, there are a couple things that we need to do. First, we can identify the elevations of the PVI and the PVT. You can see that I've already put the stationing in because each half of the curve is 300 feet. So that's fairly straightforward. So if we want to identify the elevation of the PVI, that's just 1,000 feet minus 300 times 0.035. And so I will just write that there. That's 989.5. And then the PVT is just 989.5 plus 300 times 0.005. And I'll write that over there, which is 991.0 feet. So we've got the elevations of all 3 of the component spots. We want to find the elevation on the curve at the PVI, and then we want to identify over here on the right, the low point is going to be over here. So we want to identify the station for that, and then we'll calculate the offset, which is going to be this distance. Offset is this distance. So I have the convention that I usually like to work from left to right. When you're calculating offset, you can work either way. But for me, I just stay consistent and do it from left to right. So first of all, let's find the offset at the midpoint. And our equation for that is AL over 800. So you remember that A is the absolute value of G2 minus G1 times L over 800. So this is the absolute value of plus 0.5 minus a negative 3.5. And remember, when you're calculating the value of A, we leave the slopes in integer form. L is 600 divided by 800. So this is A is just 4 times 600 divided by 800. So our value for Y sub M is 3. So we know that the elevation on the curve here is just 989.5 plus 3 feet. So the elevation on the curve is 992.5 feet. So we know that. So we next want to find the location, the x location from left to right of the low point. And you remember our equation for that is LG1 over G1 minus G2. 600 times minus 3.5. Slopes expressed as integers. Minus 3.5 minus 0.5. So the distance then from the left-hand side of the low point is 525 feet. So the station for that, we just add 525 feet to the PVC. So the station is 175 plus 25. So we're almost there. All we need to do now is calculate the offset for this low point location. And again, I want to emphasize that this offset is this distance here. So from the extension of the tangent to the curve itself. So the offset for 175 plus 25, the general equation, ax squared over 200L. So this is 4 times 525 feet squared divided by 200 times 600. So this value is 9.18 feet. So this distance here is 9.18 feet. So in order finally to find the elevation on the curve at the low point, the elevation at 175 plus 25. So we can start from the PVC equals 1,000 minus 525 times 0.035. So that takes us down to this point, and then we just go up, ship, plus 9.18, and the elevation is 990.81 feet. So now you've completely described this vertical curve, and we're done. Thank you very much for your attention.